I'm trying to finish that tonight. I sent it to you tonight.
So once you're done,
Mhm.
then I'll help you. Okay.
Yeah.
So basically,
I don't
you
think
have to
it's
stop
too much.
broadcast and then hang up the call. That's all. It's just two things.
Okay.
Otherwise, it won't be
I
saved.
think
So
you did a pretty good job.
I'll help you after that.
Okay.
So basically, you can start. If there is anybody participating, you can see that here.
Okay. But not on that screen, right?
Yeah.
Okay. Should we wait for other people?
And wait a few moments. Well, before we wait, anybody signing up?
Not yet.
Well, before we wait, while we're waiting, well, I just want to introduce our visitor. Why don't you say your name properly? How do you say your name?
Oh yeah, so my name is Satoru Okashima.
Satoru
Okashima.
Okashima. Yeah. Right. So I don't want to pronounce your name wrong. Yeah. And Satoru is visiting us from University of Tokyo, and so he's been working on high resolution atmosphere GCM simulations on swarm tracks. And so, yeah. So he's been looking at the more specific swarm tracks. Right. So he's going to give a presentation in a couple weeks. Do you know everybody here? You met Professor Salman, right?
Yes.
And why don't we go?
Hi, I'm Darun. I work with Dr. Saravanan.
And Saron is working on the aerosol.
Yeah, I'm working on the aerosol. Working on the aerosol in the model. Yeah.
Nice to meet you.
Nice to meet you. My name is Rafael. I work in the atmospheric science department and I mostly work with model.
Rafael is responsible for developing this high resolution couple problems.
My name is Jason. I work with Professor Saravanan.
Yeah.
And I am basically an ocean modeler. So I work with storms. I also work with some of the coupled cases with Mahale. Nice meeting you. To Shamu. Yes.
Because he's renting a room for Frankie.
So you're the landlord.
He's your landlord.
So if you have
have
a
to
problem,
pay him.
just let us know. We can take care of it.
Nice to meet you.
Nice to meet you.
My name is Lee. Yeah, and I work with Dr. Min Chen. And I work with ROMs and basically help to solve the modeling SST bias problem in the Southeast network.
Yeah, I think I can also pass tonight.
No, we see you know each other, right?
Yeah, we know each other.
Yeah. Okay.
I am there.
Did you try your Japanese with him?
Yeah, I
You
speak
did?
there.
Oh, is his Japanese good enough?
Yeah.
Yeah.
So I'm working on the hurricane activity. So next week is my turn to present.
Oh yeah.
So I'm Gao.
Yeah.
We have known each other.
Yeah, I'm Xiaohui. And yeah, I work on the bilateral interactions on stable contracts.
Similar to your work.
Yeah.
So I'm sure you know.
And I'm watching. I met you. Yeah.
Yeah.
So what I'm doing, I'm going to present today. So we will see.
Okay.
Let's see. Okay, so Chris and who's
Oh, you already did.
here?
Was that additional?
So just make sure they can hear us. Somebody signed on.
Did anybody?
Can you guys hear me?
Yes.
Yes.
Okay.
Yes.
Okay.
Great. So we also have two people working remotely. You know, one in California, the other one is in Anchor.
Okay, so today I'm going to talk about what I'm recently doing, focusing on how the SST bias influence or predictability of tropical cyclones, and how this bias will influence the African monsoon and its associated rainfall. So I will start with a really brief introduction because many people in our group are working on this SST bias, and people have already given presentation on it, so I'm not spending a lot of time on it. And then I will talk about my model setup, and then give you a preliminary results and a small summary. So so let's start with what is the SST bias. So the SST bias is a well-known problem in the general circulation models. So in this level of models, we tend to have a positive bias in both southern Pacific and the southern Atlantic oceans. So this figure shows the SST bias generated by 25 coupled GCMs compared to the Halley SST. And we can see that the bias in the Atlantic regions can be as high as around like 4 degrees, and it's pretty big in this region. So the most problematic thing is that this SST bias doesn't tend to be solved in a newer models. So the top two figures shows the SST bias generated by CIMI 5 and CIMI 3 compared to the Reynolds SST. So if we look at the difference between the CIMI 3 and CIMI 5 SST, we can kind of tell that the bias doesn't really decrease in CIMI 5. And if we look at the longitudinal section of the SST, we can still see both CIMI 3 and CIMI 5 has a huge SST bias around like 20 degrees west to 10 degrees east. So Desert Isle in 2010 demonstrated that the Atlantic regions had a dominant warming trend among the tropical over the 20th century. And also Emmanuel in 2007 shows that the tropical cyclones and the hurricane activity in this region was influenced by the SST trend. So if we don't consider the SST bias, we may have a problem consider the our simulated TC activities. So the model we use is WRF configured tropical channel model, which is set up by Chris. And the region of this tropical channel model is in the tropic of the globe, and is set up from 30 degrees south to 50 degrees north. So the reason we choose this region is because the first thing is that because it contains the whole global tropics, so it makes us easier to include the propagation of the atmospheric influence by the SST bias propagate around the tropics around the globe. And the reason it's set up to 50 degrees north instead of just 30 is because we can consider the impact coming from outside of the tropic into the tropic. So the model resolution is 27 kilometers in the horizontal directions. That made this model TC permitting. And in the vertical directions, we have 32 layers. And the lateral boundary conditions are coming from the 6-hourly NCEP2 reanalysis data from either 1989 or 1996. And these 2 years were picked because they have neutral climate modes such as an AMO, so we don't have to worry that the climate mode variation will influence the tropical cyclone activity. And the initial conditions is starting in April, and here are 8 dates that are listed. They are the initial dates coming from these 2 years, so that will give us total 16 ensemble rounds. So the simulation period we need is from June 1st to December 1st, which is the period of the tropical cyclone season. So for example, if for the first ensemble is starting with at April 15, so we discard the first 2 months and only analyze from June 1st to December 1st. And other than the control round, we have 3 different perturbed rounds, which are the positive, negative, and combined rounds. I will come back to this later. So the SST bias we are using is only in the Atlantic regions. We're not consider the bias in the Pacific regions at this point. And the time period we use for the climatological bias is from 1984 to 2004. And so the bias is not fixed. It's not a fixed number. It's a monthly varying number. So it has the seasonal cycle and all that. And the original monthly data was interpolated to 6 hourly data.
So it's monthly, but it repeats itself every year.
Yes. And the control SST we use is the Halley SST from 1950 to 2014. It's also a monthly climatology. And we use 37 models from the SIMI-5 to calculate the multi-model ensemble means and take the difference with the NOAA OIST product to get the bias. And then we add the bias to all the SST variables for the inputs.
When you say, probably I missed something, but you say time frequency interpolated to 6 hourly from monthly. What do you mean by that?
So the original data is in monthly.
Right.
And because we need 6 hourly input,
Right.
so we interpolate on the time direction.
There is no interpolation possible.
Yeah.
It's a linear interpolation.
Yeah, technically you can do that, but it's not like.
You just have 2 groups, one that you're charting.
And it's a month and you're trying to do 6 hours.
Right. So
Right.
just sampling it's just interpolating between 2 points.
I won't say it's really
that's
good,
fine.
but you can do that, yeah.
Yeah, but
It is a
be
linear
careful
interpolation.
when you say something like this. It's
Well, no, it is a linear interpolation.
No,
Mathematically, that's
I know you can do it. I'm not
Yeah.
saying
But
you
this
can't,
is what
but
people do.
yeah, that's people do that all the time.
but you should be able to specify that to me because it looks, I don't know,
That's how people do it.
probably because
So
it's
this is
specified.
because the Hardy SST is available only monthly, right?
I mean, the reason you have to do that is because the WRF require the same input of the
Yeah,
other
yeah.
boundary conditions and
I
the
understand, and
low
we
boundary.
do this in the data model.
Yeah.
The data model
Yeah.
works this way.
Yeah, I mean, that's how it
The only
works.
thing I was trying to point out is, 6 hours from monthly, it's a huge difference.
It
So
is,
you probably
yeah.
should specify, and then at least I would, type of interpolation you're using,
Yeah, I could just put linear.
You just do a linearly
Yeah.
interpolate.
Okay.
Yeah. Linearly
just to make
interpolate.
it clear.
Okay.
Yeah.
Well, it's pretty much the default.
Yeah.
Yeah,
I
people
know.
do that all the
That's
time.
what I did.
Why did you use 2 different SST products to find so in your data you used Hadley SST, I believe Hadley SST to find the bias? Is that?
No, that's right.
No, this is actually, some other people use HIDA SST to define the bias. So in this work, the bias was essentially referenced to the OI.
No, okay, it's not.
Right. And the reason I think we do that is because the control simulation was using the NOAA SST climatology.
It probably doesn't matter to the
I don't think it matters.
The
Yeah,
bias is so big.
the bias is so big, it doesn't
It's right? Difference is about much.
So how big is the bias? It's this big. So, so the topmost figure shows the positive bias itself, and then the bottom shows the negative bias. I just basically separate them by 0 degree. So you can see that even though the positive bias contains only a smaller region in the southern Atlantic regions, but the value is really big. The magnitude is around like 6. And then for the negative bias, it kind of spread out of the Atlantic regions, but the values are smaller. So it's like -2 or so. And
except near the Gulf Stream.
right. So in order to consider only the tropical bias, I cut off the bias right at 30 degrees, and then do a smoothing from 30 degrees to 35. So that means I take whatever the values on 30 degrees and then make it to 0 at 35. So this is the results. So we can still see that the negative bias has a larger regional influence than the positive ones, but the magnitudes are smaller. So when I say the positive runs, I mean I use this bias for the runs, and this is for the negative, and for the combined runs, I use both of them. And the top 2 figures are just showing the control, what the control SST look like, and this is the combined SST. So just ignore the values on the land because it's not SST anymore. So before we go into the results, I would like to show you an index that we usually use to look at the TC activity. So it's the accumulated cyclone energy, which is calculated by the summation of the square root of 6-hourly maximum system wind speed in knots. So this index can consider for strands, number, and duration. So it's a pretty good metric to look at the TC activity. This figure contains a lot of information. I will try to do my best to explain them.
So maybe you showed it earlier. How long are the runs?
How do you mean?
June to December. June to December. Just
April to December.
You mean this one? Oh, it's from April to December. Sorry.
No, it's almost 16. Yeah.
So I separate them into 3 regions, which are the African plus Atlantic Ocean, the Eastern North Pacific plus America, and then the Western North Pacific plus Asia regions. And the numbers are the ACE, the accumulated cyclone energy, the number of tropical cyclones, and also the lifetime. So the life here means the average lifetime of a tropical cyclone, and it's in days.
How do you define the cyclone in this simulation? Do you have some sort of standard?
We have a tracking algorithm. I'll talk about that.
So it has to be some above some particular wind speed.
What do you mean by?
So how do you identify a cyclone and define a cyclone in the model?
We use both the wind speed and also the warm core definition.
So
not just the wind speed.
It has to be above some value, right?
Sorry.
The wind speed has to be above some value, I guess.
Right.
What is that number?
17.5.
Oh.
17.5.
17.5 knots. Okay.
but for
No,
Mars,
knots. Meter per second.
Meter per second.
Yeah.
So from top to bottom, there are the control runs, positive, negative, and combined runs. And the color red for the numbers means that it is significantly different from the control rounds, and it's passing the 95% student t-test. And the grids that failed in the color means they are significantly different from the combined rounds. So the red one means it has.
What is 8 and 16? 8 and 16?
Oh, because I have totally 16 ensemble rounds, right?
Right.
And eight are from 1989 and 8 are from 1996.
Right.
So I would like to see if the lateral boundary condition will influence the results.
Okay.
So I calculate the numbers for only the first 8 ensembles and the total 16 ensembles. Okay, so if we look at the number, we can kind of say that the positive rounds, I'm looking at just the Atlantic regions. So the positive doesn't really differ from the control rounds. But the negative, in the negative rounds, we can see a dramatic decrease in ACE and number of tropical cyclones, and also in combined. But the value is not as low as negative. So it's like a combination of the positive and negative rounds. And
so in the combined, you don't have any color. So does it? What does it?
Because the failing in the grid means it's different from combined.
Okay.
Yeah, so the combined itself cannot be different from combined. So it's not failed, yeah. Sorry for the...
And you may want to split it up and present it again.
Yeah.
Too many.
Yeah, I think too many.
I get it, but it took me a while.
Yeah, too much information.
Too much information in one slide.
Yeah, I will try to separate them.
And you could also maybe split it into multiple slides. Just talk about first maybe about ACE and then bring in the others.
Yeah, that would be.
And also, I don't like to see the number. Sometimes I think a bar graph or something may be easier to see.
Right. Or like
the
a circle or
numbers,
something. Yeah.
Yeah.
Yeah, I will do that
Yeah.
next time. Yeah.
I'm just ignoring everything there and looking at one column.
This is for all the cyclones in the Atlantic basin, right? Irrespective of where it ends up. It starts in
No, there's Atlantic and
Starting in Atlantic and Africa.
And then
and then East and North Pacific, they're all there.
there's a Pacific here too. I think.
I think everything, all the results are there.
Okay.
Just no Indian Ocean. Okay, and if we look at the Eastern North Pacific and the American regions, we still don't see a huge difference between control and positive, but there's a large increase in both negative and combined simulations.
So the positive, there's a little bit in the Northern Hemisphere, right? Can you look at the positive and all? Just curious.
Stir it up.
Not really, just a little bit.
Very little.
Yeah.
Yeah, but that may, I'm just trying to figure out if that's the one that, I think that positive is making a difference. Is it the Southern Hemisphere positive or the Northern Hemisphere positive? Because Northern Hemisphere positive, right, in the MDR.
Yeah, right. So the MDR is.
I mean, initially I thought it was really the shift of the ITCZ that matters,
Maybe.
but it doesn't look that case.
It seems to make a small difference to positive.
Right.
But I suspect if you had enough big ensemble side, you'd see it.
Right, so it's very surprising. The bias is very large, but
Yeah,
the,
it
in
is.
terms of impact on the hurricane, actually it doesn't make much of a difference.
But it's in the Southern Hemisphere.
So you're saying that that small part is making.
No, I'm not saying it. I'm
Okay.
just looking. I was just trying to figure out how big it is. It's really small.
Right.
Mhm.
It's kind of surprising.
Because you talk about warm, positive and negative, you could also have done Northern Hemisphere and Southern Hemisphere. Probably similar results.
I mean, the whole study was motivated by this presentation by Vicky, presented in Qingdao last summer. You know, he built this hurricane forecast, seasonal hurricane forecast model at GFDL. Now he's actually using flux correction. Because if he doesn't get flux, if you don't do the flux correction, you don't get any hurricanes in the Atlantic Ocean. So we were really
But doing
curious.
a couple.
In a couple of models, yeah. You don't see any hurricanes in that model. So only after they made a correction to flux spring, you start to see hurricanes appearing in the Atlantic Ocean. So you can't do any forecast if you don't have any hurricanes. So then we're trying to figure out which bias is actually more important.
So
And I have a question about this life. I mean, you know, we in the model we use both criteria. We use the warm core criteria and the surface pressure or the wind criteria, right? Now, in reality, when people tracking hurricanes,
we don't use
we don't use the warm core criteria, right? Because we don't have any condition for that.
Right.
So how are you going to reconcile that? I mean, it's difficult to compare with observations, right?
It is, yeah.
I mean, isn't that going to be a... Anyway, we can probably talk about this.
Yeah. Okay. So come back to the Western North Pacific. It seems that the bias in the Atlantic Ocean doesn't really influence the tropical cyclones in the Western Pacific regions.
Is it any difference in the peak intensity or something like that? When you put the negative,
So can you
just
say that?
number of the strongest category 4 categories.
I didn't look into the PDF yet.
It'd be interesting to look at the PDF.
Right.
Yeah.
Would be
Sometimes the
interesting.
tail is affected differently.
Yeah.
And so the other way to look at the tropical cyclone activity is look at this matrix called the Genesis Potential Index. And it uses the environmental variables to calculate the tropical cyclone possible tropical cyclone activity. So it's not using anything from the cyclones itself. So this index is calculated using the absolute vorticity at 850 millibar, the relative humidity at 600 millibar, and the potential intensity, which is a function of both SST and vertical profiles of atmospheric temperature and moisture. So we can guess that this term will influence the tropical cyclone activity a lot in our simulations because we add in the SST bias. So the last one is the vertical wind shear between 850 and 200 millibar. So these results are coming from only the first 8 ensembles, which is from the 1989 lateral boundary conditions. So the 3 figures shows the difference between combined positive, negative, and control runs. So it's the GPI difference. So we can obviously see that both the combined and the negative runs give us a negative anomalies in the Atlantic regions, which is corresponding to a decrease in ACE. And in the Eastern North Pacific, we see a positive anomaly in both combined and negative cases. That is also correspond to what we've seen in ACE. And we don't really see a lot happening in the positive runs. Maybe there's a little bit increase, but it's not too much compared to the other 2.
But the relation is opposite, right?
Yeah.
Yes.
It's opposite.
Yeah. It should be actually the same, but actually it turns out to be opposite.
Right.
Opposite in this.
And if you compare the negative versus that, I mean, that's small, but it's, at least the signs are
Right.
the
Still
colors are
different,
reversed.
yeah.
So the positive is actually trying to cancel some of the negative bias.
Right. And that's what we see in ACE as well.
We believe you're showing track density.
Yeah, I will do that. Yeah.
Did you actually put in did you do a statistical test on this?
No. Yeah, I should do.
But I wouldn't expect it. I mean, it's pretty far away from where the actual positive bias is.
Right.
Just curious, but
Well, initially we saw that the positive bias may have the effect on ITCD, could shift the ITCD southward. So that could have some effect on the wind shear, right? So as a result, it might have some impact, but it turns out that wasn't. It's really interesting. Later on, it's just going to show that the most impact is actually over the West Africa monsoon. Actually, there's some really interesting impact. It looks like on easterly waves.
So this pattern, right, is it coming from, you had 3 terms, right, in the previous DPI? You had absolute vorticity. Can you pin down why is it over this region? What's causing it?
I will show that.
Okay.
Yeah. So this is from the 8 ensembles, and this is from the 16 one. So you can tell that there's no much different. So it's a good thing because that means the lateral boundary condition doesn't influence our results for the tropical cyclone activity. And this is showing the relative humidity at 600 millibar. So basically, if we have lower RH, it is less likely for tropical cyclone to generate, and vice versa. So if we see a negative anomaly in RH, that means a positive in GPI, basically. So so in both combined and negative runs, we see a negative anomaly in Atlantic regions, which is corresponding to a negative anomaly in GPI. And the interesting thing is that we see a little bit negative here in the Eastern North Pacific, but we have a positive GPI and S there.
So actually, this blue color, this to an extent, you can relate it to your this biases also.
Sorry.
It's like because you have a cold SST, so it's in a
right.
similar region.
Yeah, right.
But there's a warm patch over the North Pacific, which the North Pacific.
This one?
Yeah.
Yeah.
Don't know. Is that significant or?
I should have done it.
that is the biggest signal.
Yeah.
Yeah.
It's interesting, isn't it?
Yes, I would not have expected.
I was wondering it has something to do with the Rossby waves. Effects. You have this forcing in the Caribbean, and they actually exposing Rossby will probably westward. Could be.
How do you configure the control, the positive versus the control? What's the main difference? SSTs. It's only the SSTs.
Yeah, only the SST.
The other things are essentially.
They are all the same. Yeah.
So you think that the actual moisture of RH that you see in the tropical Africa, the equatorial Africa, it's due to mostly the SSTs.
Yeah, that's what I thought. Yeah, because we have the bias over like here, so it's really very possible.
So the negative, and just I can't remember now, the bias in the west coast of Africa. How is it? It's cold or it's almost the bias.
You mean here?
Yes.
There's
Just go back to the
no more, not much.
Bias
Oh,
match.
there was not much, right?
Not much.
So it's
Very little.
Yeah.
Very little.
Yeah, there's a little bit positive here and negative here, so not much.
So there is a local signature, but there is also
right. So this is the 16 ensemble things, and still there's no much difference between 8 and
I was
16.
wondering if you add a positive and a negative together, you probably get a 0 net.
You mean just
redistribute the moisture. The decrease over here and then increase over there.
You mean just linearly adding
No, it's
this
just
two?
taking area average.
Oh, okay.
The net change is probably very small.
It's possible. Even in the combined runs, I think maybe
Right,
they
if you
can,
add the
they
negative
cancel
and
out.
positive together, it probably
Yeah.
cancels.
Now, even in positive, even this has come up, the on the American coast. This was not very strong. The South American coast in positive. Yeah, just at the coast. That was very strong in the state.
So then this is showing the 8 ensembles share between 850 and 200 millibar. And so when we have a huge share, then the structure of tropical cyclone cannot maintain, so we tend to have a lesser tropical cyclone activity. And so we see a positive share anomaly in Atlantic regions in both combined and negative runs, which is corresponding to a decrease in GPI and ACE. And then we see a negative anomaly in the Eastern North Pacific in both cases, and it's corresponding to an increase in GPI. So that means the shear effect on the GPI might cancel out what we've seen in RH in the Eastern North Pacific region. So we see a little bit negative here, and which should give us a less GPI, but then this effect is canceled out from by the shear effect, and this effect is more dominant than RH in this region. And this is showing the 16 one. We can kind of see there's a difference in the boundary, in the lateral boundary.
Is the 16 noisier than the 8?
Yeah.
That is unusual. Should be expected. Less noise.
But the A1 is coming from the same year.
Oh, okay.
Yeah, that might be why.
That's-
But
Can we go
if-
to the 16? That's a lot of noise.
yeah, but if you
Pattern is similar, right? It's
yeah,
just
if you
bigger.
focus
extra-
on just this
Yeah,
region,
it's just extra
then it's
value.
really similar.
If you do a pattern color, you can probably get a very high quality.
Yeah.
But it's just the value looks a lot bigger.
Right, because I use the same values, I think. Yeah, to see the difference.
So it adds noise only in the region far away from region of interest.
So one thing we should note is that even though we don't see a lot variability in maybe Atlantic and Eastern North Pacific, we do see something on the African land in positive ensemblings. Maybe we should look at the 8 one. It's more obvious that we have something on the African land, but not really huge stuff inside the MDR regions.
So I remember you mentioning when you showed that big table, you showed that in the GPI, when you did the ACE, the way I remember is that the positive had a bit bigger impact than the negative.
I think, what do you mean by impact?
No, the
Negative.
negative.
The negative is,
Positive are very small.
yeah,
Positive
it
is very
doesn't really differ from the
Positive and the
controls.
control are very similar.
So okay.
Yeah.
Now it makes sense.
It's very small.
Yeah. Here. And then
So just one comment. You plotted shear and relative humidity, but if you plotted them in GPI units, like putting it in the formula, then it might be easy to compare the magnitudes.
yeah,
You really should.
So you put that in the GPI.
Percentage decrease or increase or something.
So these are
The
different units. You have
contributions.
1 year,
Yeah.
you have relative
Yeah.
meters per second.
Yeah.
I agree. I agree.
How would you do that? How would you put it in GPI?
It's a little tricky, but you just take the control
so-
and then you add and add.
You're assuming it linearly add together.
yeah. So like we have these variables, right? So I can fix like this one to control and then change this
Okay.
one, and
Just
So-
one, just one.
Yeah, right.
You're actually trying to do something, you're taking the log, right?
Yeah,
You're taking the log because it's all product. So if you
That's
take the
true.
log of this, it's become active.
That's true.
So you can individually add each component together.
So what if I just do, the first term, the magnitude of the first term, the magnitude of the second term, third term, and fourth term? Why wouldn't that give me the relative?
Well, actually, each terms, it's in the difference. Maybe.
their orders are pretty
Oh,
different,
okay.
so we cannot
So
just
the
do that.
products, not a linear relationship.
It's a nonlinear relationship
Right.
because they're products of this thing. If you take the log, you can linearly add.
To look at
Yeah.
the difference.
Yeah, makes sense.
Look at the
You
difference.
take the log, yeah, then you can add everything together.
Okay, so then we're looking into the track density, and I was trying to show if the combined round is the linear combination of positive and negative rounds with the track density. And the algorithm we use is from Wash 1997, and the tracking core code is written by Jinshen. And then the resolution we use here is 2 degree by 2 degree. And the unit here is the storm day. So because we have outputs in 6 hourly, so if one tropical cyclone's passing one box just once, then it's count as 0.25 instead of 1. So that makes the unit into storm day instead of like times or something else. And we're not including the Indian Ocean at this point. And so the longitude region we use is from minus 270 to 40. So it's not including the Indian Ocean. So this is showing the 8 ensemble summation of the track density of control, combined, positive, and negative. So we can kind of see that the negative pattern looks really similar to the combined one. So we see lesser density in the middle of Atlantic Ocean and larger density in the two sides.
It's confusing because the biggest signal is in the Pacific. So it's kind of, the eye goes to the Pacific, not to the Atlantic signal.
Yeah.
The Atlantic is in the.
Because we see an increase.
Maybe we can change the color scheme.
Oh yeah, right. You mean seeing the this
So
part?
white and blue, and change it so you can see the Atlantic.
Yeah. Yeah. And then the positive pattern looks really similar to the control one. This one.
So do you account for the hurricane speed when you compute the track density?
Speed?
Yeah. So you count per grid box and like hurricane track. What if a hurricane is super slow?
It's
It's
super
very-
slow, then it will count many times.
Many times.
Yeah.
Then I think we're taken care of. We can just stay in the same box.
Ideally, that's wrong, right? I mean,
No, that's just, instead of moving to a different box and stay in the same box. So
I think it kind of depends on the resolution you choose. So if the box is bigger, then
so
it's more likely.
it's slightly tricky here because basically we'll associate these colors with like a more number of hurricanes, right? So if there is a region where hurricanes are slower and there is a region hurricanes are faster, then the region where hurricane is faster will always have like a lower number of counts.
Yeah, but it'll be a bigger area.
Yeah,
so
right.
It'll be over a bigger area. So it's kind of average out.
I don't think this problem with my getting stuff. That's why.
Just to track density is a little bit tricky. Some guys even define 8 degree times 8 degree. Some guys 2 degree times 2 degree.
So if I have to relate this to my GPI or AS,
You can't relate it to GPI. GPI is a very.
GPI is
It's
an
environmental-
environmental variable. So
yeah.
it's something that
so
is
what does GPI tell when there is more chance of hurricanes?
Yeah, more chance.
Hurricanes forming.
Yeah.
This is not
Possibility.
The environment that's favorable for
the genesis. the actual tracks. So we develop.
And ACE is.
ACE will be a little closer.
Right.
So that's one number though.
Right.
But it,
Yeah,
you can't have a
ACE
station.
density.
You don't have a station.
So how does the real hurricane track look like? I mean, forget about these extras. How does in reality look like?
In the track density.
Yeah.
So in model validation, so validating this control run.
Yeah, just to make get a feel of how realistic is the pattern, spatial pattern in the model.
You did that, right? I think
Yeah.
Chris has done that.
Yeah,
I
that's
see.
good for the revised paper.
Chris did it for the revised paper.
Well, the real tracks tend to go more towards the Gulf of Mexico. This one,
Yeah.
models tend to go north too early.
Okay.
Yeah, it tends to be too much in the Gulf of Mexico and not quite enough in the main development region.
Mhm.
Right.
And the Pacific part is over represented in the model.
In the Eastern Pacific
Yeah.
part. Can you say your question again?
So my question is like, if you plot the real track density, do you see the higher values in the Atlantic, Gulf of Mexico region, or in the Eastern Pacific Ocean?
I think we see more in this region.
Yeah. Eastern Pacific is
Eastern Pacific is pretty
very
high.
high.
Okay.
Of course, the track is more focused, more concentrated. So in each box, maybe much more tracks pass through than that.
You'll hear more next week, and he's going to actually talk about Eastern Pacific. So you're going to hear another one.
So this is
So
the
the overall numbers in the Atlantic are right, but the spatial pattern has some biases.
Right.
so there's still no much difference between 8 and 16 rounds.
I have a quick question. So
Okay.
why is my positive more close to control, whereas my negative? You mentioned it, right? Why do you think it be more closer to those the
The
negative?
positive makes very little.
The positive bias doesn't have much effect on a hurricane.
Okay, and that's
So the main range.
so the control
The
doesn't
control
have
has no
bias.
bias, yeah.
The
Control
control
is
has
the
no bias.
perfect
Yeah.
pathological SST.
Okay.
So the main
And
reason
we
might
made
be.
SST worse, so make adding the model bias to the SST just to see if you're running the model, the climate model,
Okay.
what kind of a bias would have
In
impact
this,
on
in
a
this plot, bio is actually not even in this plot, it's in the southern hemisphere.
Right.
Yeah.
Right, it stops at the equator.
So one possible reason is that the negative bias is right on the main developed region of tropical cyclones in Atlantic Ocean.
So to some extent, it's a good news for the people running the GCMs. They don't have to worry about
Yeah.
the nasty wound bias.
Yeah.
They can still say the hurricane's probably okay.
So the GFDL model has a bad bias in the North Atlantic. That's where they're.
Yes.
Mhm.
Yes.
That's
GFDL model has a less warm bias, but a strong cold bias to the north.
That's why they need construction.
That's why they don't have any hurricanes in there.
That's why they need construction.
Well,
Yeah.
they invented flux correction.
That's right. So that's why they need to use the flux correction to get this thing back. Otherwise, they don't simulate any hurricanes.
So in order to look at the linearity of the positive, negative, and combined rounds, I plot out the difference between positive, negative, combined, and the control rounds. And this one is just adding the top two, so it's positive plus negative minus 2 control. So if it's linear, then we should see a same patterns in this two, but it doesn't give us a same patterns. I will.
Similar.
Yes, similar, but it's still similar to the negative one, so it's not exactly the same. Yeah. So at least we can say that the combined results is not just the linear combination of positive and negative rounds.
By the way, the quality of your plots seem to really
Yeah, it's
bad.
really bad.
Why is that? Is that the projector is bad or it's actually?
I'm not sure.
Did you copy it from PDF file?
Did you copy from something? Whatever the
Actually,
software
I
you
cut
use.
out with MATLAB and then I use Illustrator to combine them. So that might be the reason why.
What was the starting image format? It was PNG, JPEG, or PDF?
EPS.
I think I use EPS because I tried PDF. The resolution is better, but it cannot properly show out the
How do you
code.
convert the EPS? How do you put EPS in PowerPoint? Do you convert it to PNG or JPEG?
I just use
JPEG first.
Yeah, but I still use EPS.
Adobe Illustrator.
Illustrator.
So the best way is like, I always do with PNG and then use a convert command. It's a command line tool. You can join any number of figures any way you want, left or right or like.
Oh, okay.
Why you have a problem with
then
inputting?
you won't lose any resolution. You can get the figure the same resolution that you started.
When I save it, I guess I use normal to plot this,
Anyway,
and then
let's
when I save it,
worry
the
about
color bar
that
is
later.
not properly show up. It's all in black. or
Just
something.
if you want to give a presentation, a conference or something, you need to
Yeah,
find
I
out.
cannot use this kind of thing.
Yeah, it just looks really bad.
Yeah, I know.
When you save initially itself, you can change the resolution also. There also.
I know, but yeah, it's not the resolution. It's the color not showing up. Yeah. And this is the 16 one. So yeah, kind of give us the same thing. So I'm not talking about this. And this is just showing that the track density in the Western North Pacific looks similar between the 4 rounds. So there's no one rounds that turn out different from others. And as we just talked about that, so both negative and combined rounds give us a huge difference in the tropical cyclone activity compared to control, but not the positive rounds. But we do see a sheer difference on the African land in the positive rounds. So if we look into the literature, there are a lot of people focusing on how the variability of ST can influence the rainfall in the East Atlantic region. So, so it is known that the SST distributions and even the global distribution can related to the variability of the Western African rainfall. And also the SST in the Eastern Atlantic region, especially the Gulf of Guinea, can influence the precipitation over the Sahel region. And then the Atlantic SST is really important for predict the variability of rainfall over the Guinea coast. So then we want to look at the rainfall patterns. So here we start with compare our rainfall output with the observation. So the toppest one is showing the observational rainfall from GPCP 2.2, and it's only from June to September. So we can, so this one is the 8 ensembles from control rounds, and this is the 16 ensembles. So we can see that the rainfall magnitudes are basically much larger than the observational data.
So more than twice.
Like, yeah, like twice, yeah.
Could it also be because of the sampling? And there you're making averages of almost 21 years.
Yeah, but we have like 16 ensembles.
Yeah,
so
16, okay.
it shouldn't be that much different.
No, but
Yeah, I don't think.
I guess because we're using control SST, right?
Yeah.
So the rainfall becomes nonlinear SST, observation SST, and the
Right.
But
Yeah,
I guess
that's true.
This Kent Fridge, right? Kent
Yeah,
Fridge.
Kent Fridge.
Kent Fridge is known to be overactive.
Mm.
And the other thing I'm more concerned is the maximum. I mean, in observation, you actually don't see this maximum rainfall. It's just of the closest Central America. Right?
You mean
Yeah.
here?
Yeah.
GPCP is it what, 2 degrees?
Yeah, GPCP, I was wondering how accurate is GPCP? Why don't you use trim or something?
Yeah, trim.
Trim would be, I mean, you're looking at the tropical domain, definitely should use trim. And then, in fact, I was just looking at the trim and GPM. If you look the mean rainfall, it differ by a factor of 2.
But GPM is higher.
GPM is a lot higher.
That's
So if you look at it, maybe the Cambridge is not that bad.
If you wait long enough, your model becomes.
Yeah. If you wait long enough, we're just smarter than the data, I think.
What is GPM?
Global precipitation measurement.
It's
It's a
It went up
replacement.
over the year previously.
It's a 10-kilometer resolution data set. It's quite surprising. It's much stronger.
You think GPM is better than trim?
It should be, right? If it is a replacement for trim, I mean, it should be better, right? You can't replace something.
So they let it retune all the GCFs.
I think so. I mean, but it is by a factor of 2, really.
So this is showing the seasonality of the observation and the control run. So the 4 figures showing the difference between June, July, August, and September with the seasonal mean from June to September.
So which one is, I can't even read the things now. I mean, which one is positive? Oh, this is for different seasons.
So this is June minus the seasonal mean, July minus seasonal mean.
Okay, and this is for combined bias?
This is for the observation, and this is for the control.
Oh, okay. So it's a seasonality. So it's just subtracting the annual mean.
Not annual mean. It's the mean from June to September. So seasonal mean. Yeah. Yeah. So I just want to show that even though the magnitudes are different, the seasonality seems kind of similar between the observation. Sorry?
The scale is different though, right?
Yeah.
Color scale.
So I'm not looking at the
Structure.
scale. I'm just looking at the patterns.
So in observations, if you look, you can see clear change from June to the
July?
September.
September?
Yeah.
Yeah.
There's a shift. Like there's a warmer colors become the.
You mean this part, right?
Yeah.
Yeah.
So if you look at the whole ITCZ thing, you can see that.
Yeah, right. Yeah. Because we do have that different in reality. Yeah. Well, we can kind of see here as well that we have a maybe negative here and a positive here. A little bit, maybe. Yeah. And this is showing the seasonal, which is from June to September, ran different from combined positive, negative, minus control. So we do see a large positive anomaly in the African land region in positive. And we do see a little bit negative and maybe some positive here on negative, but it's not much compared to the positive one. So that means the combined one more tends to similar to the positive one, I guess. And we do see the rainfall difference in the Atlantic and Eastern Pacific regions in both combined and negative, but we don't see a lot in the positive case. So it's kind of corresponding to what we see in the tropical cyclone activity.
Do we expect the ITCZ to move down just because of these?
Move down?
Means do we expect just by changing the biases it would affect my ITCZ position?
It's
Change the
possible.
gradient.
It does because and this is just in just changing in Atlantic is doing. You can see the response.
Yeah, just you get a strong Pacific response for the negative.
Mm-hmm.
And then this is the 16 symbol means, and still not much different. Okay, so this is the Hofmöller plots, averaging the rainfall from 10th degree east to 10th degree west. So it's like this region. And the line here is the coast of Gini, so it's like here. So the X level shows the latitude from equator to like 20 degrees north. And then the Y level shows the time. So it's from June 1st to October 1st. So in reality, we should have an ocean region before June. That means we have more rainfall around the coast in the ocean, and then it will shift to the land. So for this case, trim, it shifts to the land, I think it's 1st of July, right?
Is it the same year?
Yeah, it's the same year.
This is just particular 1998, right? This is just for 1998.
I'm not sure what year is this.
Hmm?
Oh, it's 6 year mean.
6 year mean.
Yeah.
The trim is 6 year mean?
Yes.
Okay.
Yeah. So this one is their own model simulation, so we're looking at other ones. Yeah, so, and then...
I don't know why they write that.
It says 1998 here,
Yeah.
but it could be just using 1998 as the label. Yeah. Yeah. But I don't understand it.
They do it for all of them. They tell once a year.
Weird plot.
Strange plot.
And then the maximum of the rainfall will come back to the coast after the monsoon season. That's what we usually see. But in our results, we don't really see the ocean region. So we don't see a lot around the coast or inside the ocean. It's just on the maximum, it's like, I don't know, 10 degrees. And then we do see a like jump from 10 to like 12 in all cases. Yeah, but we still don't see the jump back of the maximum.
And much greater magnitude.
Yeah. And then I took the difference between combined positive, negative, and control. And we see an increase of rainfall near the coast and decrease of rainfall on the land in both combined and positive cases. And this is similar to what Vizzi and Cook found in 2001, that if we have a warm bias near the Gulf of Guinea, we tend to have increase of rainfall around the coast of Guinea and decrease of rainfall on the Congo land. So it's similar to what they have found. So in the negative case, we basically see a negative rainfall of the land and the ocean.
So go back to the previous one. I'm really curious to know. There's some. This is based on 16-member ensemble, right?
Right.
So you see this very interesting high frequency stuff.
Actually, I talked to Chris about this.
What is this?
And she thinks it might be the signal coming from the easterly wave. Because the easterly wave period is from like 2 to 9 days, which is corresponding
So is
to...
it in phase for all the ensemble members?
Yeah, that's really surprising. I mean, isn't it easily wave instability waves?
But
I mean, if it is if you randomly perturbing the atmosphere, I would expect that this thing will
Cancel out.
fire out, yeah, randomly.
but we still see this in observation. So,
Yeah, but it's observation. You only have one realization. You don't have 16-member ensemble.
but if it's like 6 year mean, it should cancel out as well.
But how do you generate the 6-member ensemble? It's different initial condition, but the same,
Yeah.
Same
same
boundary.
boundary condition.
Yeah.
That's why I think boundary
Like, maybe the boundary condition determined the
boundary
phase
condition
Yeah,
is
rotation
just
rather
because
than
it's in
the.
phase for all.
It's very possible. So maybe the signal coming all from the same boundary condition.
You have 8 and 16 for this case.
No,
So
sorry.
that'll be the case. If you looked at the 2 8s, they'd be different.
Okay.
If
Well,
you-
what's the period of this?
Oh, what do
Did
you
you,
mean?
what's the oscillation period? It's about the 2 days or 5 days or something?
It's like,
Events by
you mean
events.
here?
No, in all of them, you see the high frequency stuff.
Oh, it's like 1 week.
About 1 week.
Mm. So it's corresponding to the period of Easterly wave.
So this is for 8 or
It's
16.
shorter than 1 week. If it is 1 week, we should see only 4 of them between two markings, right?
Yeah, it's probably shorter than 1 week.
It's
I think it
shorter
should
than
be,
1 week.
yeah.
Five
Yeah.
days.
You should see only 4 of them between October 1 and September 1.
But it's still inside the period of Easterly wave. So
But this is for 8 or 16?
16.
Might want to plot it separately for the 2 8.
Okay.
Yeah, it's a quite a striking that even up to 16-member ensemble.
But
You
with
still
only
see
2
it.
different boundary conditions.
That's
Right.
true.
Mm.
That's true.
I guess one thing to note about this, though, is that it's possible that it's coming from the northern boundary condition, but the precipitation rates can be really, really high for just an individual system. And so even though some of these precipitation events look really strong and it suggests that it may be happening in multiple ensemble members, it's possible that maybe 1 or 2 are having a very, very strong precipitation event that's making these high rates that we're seeing. But I think it's probably still a
That's
good
really
idea
why I
to,
think we can probably look the 2 ensembles separately, right?
yeah, I think it's a good idea to check between the first 8 and the second 8.
Yeah, because the 2 has a different boundary condition,
right.
so that will
Yeah.
tell something whether it's coming from the boundary or not.
Yeah, I could see it going either way.
This is general.
Yes.
Yeah, but there's some she's arguing the same from the north.
Can it get to that far?
Yeah.
That seems.
Oh, that's a good question.
That's a very good question. I mean,
But
Unless it's
because I
something-
guess Chris's point of precipitation is pretty noisy field. You need a lot of average.
but that surprises me because this looks like a really deterministic frequency here.
But actually, if you look at say precipitation over the whole basin for a multi-ensemble set, a lot of times you can see an individual hurricane in the precipitation field, and it was dumping a whole lot of precipitation, and so even in the ensemble average, it shows up really clearly.
Yeah, but this is a very looks like if you do a spectrum analysis, I would expect you see probably a pretty significant peak in spectrum.
No. This is not oscillatory.
It looks to me like oscillatory.
No.
I think it's sort of hard to eyeball that.
A couple of days, we can do a spectrum and take a
Well,
look.
one thing to just draw a line at 12 north and plot time series.
Yeah, and do a spectrum analysis. Let's take a look at how strong.
Let's just look at
Well, I would say if you look at a Hofmahler plot of either the two averages for each lateral boundary condition set, or look at individual ones and see if they're similar, because we've seen before in regional WRF where the lateral boundary condition is prescribing disturbances coming in, you can actually see the precipitation propagating in the same location at the same time in multiple ensemble members. So that'll be one way to check. That's probably pretty quick.
No, the time series will tell it to you right away. Plot the 16 time series at one point.
Mm.
Just take one point there.
Like 10 degrees.
Yeah, that's actually.
Take 12 north, take its cross section, and plot all the 16 time
Oh.
series. Then if they all line up, then you know they're in phase. If not, it's just a few events dominating.
Right. Well, Raffaele has a good point, though. I mean, this is a channel model, so
That's
the boundary is pretty far away. I mean, it's a 50 versus 50 and 30.
30, yeah.
That's true.
And I'm not sure how much moisture is actually, and the summer season is not very noisy season, at least not in the northern hemisphere.
But it's pretty easy to figure that out.
We can try to figure it out. But I was really stunned by seeing on some average you still see something like that. Anyway.
I think maybe the spread of the ensemble is not big enough. Because
That's the question. Why is it not big enough?
Yeah.
You start from initial conditions, right? Initial conditions. How long do they live?
Initial condition is different by 1 day.
Yeah.
So the atmosphere instability should be
2 weeks.
definitely
2 weeks.
different.
enough to
and then,
generate
so then
enough.
you get the same. What about the same?
No, and you
No.
get random.
No, you can that's the reason why we can't make the weather forecast. So
Is the random
so-
spread big enough? Because you're going to integrate for a year.
No, but it's completely
No.
random. You lose all phase correlation.
Actually,
the atmosphere basically loses memory in a couple of days.
Right.
So there's no correlation between one to the other. When you perturb initially.
Yes, I agree with that.
Yeah.
But I wonder if there is some sort of mode develops and that more or less it's the same.
Well, even if there is some mode, the phase would be randomized.
There are more. These two waves are more.
Right.
Phase
But the phase would be randomized by the disturbances. At least theoretically, you should expect that. So you would expect ensemble average give you essentially nothing, but
Yeah.
this is kind of a really organized stuff. Anyway, go on. We can't
Actually,
figure it out now. So.
This is the last one.
Yeah.
So this is the small summary. So there's no big difference between 8 and 16 ensemble rounds, which is a good thing. So that means the lateral boundary conditions doesn't influence our results a lot. And then in both negative and combined rounds, we see a decrease in TC activity in Atlantic regions with an increase in TC activity in Eastern North Pacific and not much in the Western North Pacific. And the decrease in Atlantic corresponds to a negative anomaly in the RH at 600 millibar and a positive anomaly in share. And the increase in Eastern North Pacific corresponds to a small region of negative RH, but it's compensated by a large negative anomaly in share in that region. And the track density plot shows that the combined round is not just the combination, linear combination of positive and negative simulations. And so the first point that the WRF tropical model is simulated rainfall too heavy in tropics. Maybe I should compare it to other observation as well to see if it's still the case. And the monthly variance or the seasonality are well simulated in the model. And we are lacking the ocean region of the monsoon. And from the molar plots, we can see a dipole of an increase of precipitation near the coast and a decrease on the land, which is corresponding to what BZ and Cook found out. And that's it.
Okay, good.
Thank you.
So I think there's one comment that, even though you did this separation between the cold bias and the warm bias, right? In reality, the warm and cold bias itself may not be independent of each other.
Right.
So we actually did an experiment where you're actually just generating a warm bias in the southern Atlantic Ocean. And it turns out that the couple model actually also produce a cold bias to the north. So if that's the case, the warm bias still can have impact in a couple model. It's just not in the direct way. Other questions? No? So next week is you?
Yeah.
Okay. Chris and who? Do you have any questions?
No.
Okay.
No, I don't have any more.
Okay. Good. So we'll see you guys next week. Actually, next week I won't be here. You can do that.
I'll be here. Yeah.
You can take the cookie box. You can take the cookie box.
The most important thing, right?
Yeah. Do you have a key to this room?
No, I'll get it from the office.
So Chris, are you leaving next Wednesday too? You probably won't be able to attend either, right?
Yeah, I'm leaving Wednesday.
Yeah. So hopefully, Chris, maybe I'll see if I can talk to you later part of this week when we get this manuscript things finished.
Okay, yeah, I've started pulling together figures for the poster, so
Okay.
maybe by Friday we could talk.
Yeah, maybe Friday we can chat.
Yeah, I noticed I wanted them uploaded by tomorrow, but that seems a little bit early.
Yeah.
So.
Will the poster also be uploaded by tomorrow?
Yeah, something. I mean, I don't think you need to be.
Hey, Chris, the poster has to be uploaded by tomorrow?
That's what they asked for.
Part-time
Okay.
people,
I don't think it has to be the absolute finalized version, but
it's going to work 2 days a week.
I mean, I think it's to give people a chance to look at them before they show up. But I think everybody's busy working on posters and not going to be looking at anybody else's. So.
Very, like too far early, I guess.
Okay.
What's that?
This is too early, I guess. This is all.
Yeah, it's too early. Yeah.
Yeah.
I would say so.
Yeah.
Should I?
All right.
Yeah, we can try.
Okay, bye, Chris. See you.
Okay.
On,
See
Friday.
you Friday.
Yeah.
Okay. Bye.
Bye.
That's right. This week.
June 15th.
Yeah, I want to do that.